Okay. So when you have the honor of introducing a keynote speaker like Ruhi, you always try to find a unique way to present that person. And while thinking about it, it occurred to me that this morning is all about the future of web and internet and possibly the impact of AI on that future. And therefore, in the future, we could imagine that distinguished keynote speaker would not be introduced by people like me, but they may be introduced by digital assistants, such as the one Ruhi creates. So in other words, to introduce the keynote speaker of this morning, who better than the smart speaker he helped created? So right now in the room, a lot of people are saying, no, he's not doing a live demo in a plenary. He's saying, yes, he is. It's even worse because I've been selected as a beta tester for the French version of Alexa, and that's it. So let's see, now I have to play with technology. Alexa? Hello.
Good morning, Fabian. How are you doing?
Honestly, a bit nervous. But by the way, when you introduce a keynote speaker, a very good thing to do is to engage the audience. And one of the ways to do that is to make a joke. And this thing knows to make joke. Let's see. Alexa, tell me a joke.
Why did the web developer go broke? Because he used up all his cash.
Okay, the joke did work. Okay. Oh, I'm sorry. Wendy, you'll have a whole panel to tell me about how sexist I was. Oh, I'm sorry. But you must give to me that it was a very appropriate joke for a web conference, wasn't it? Okay. Okay, let's be more serious. Alexa, what are you?
I am Alexa, a digital assistant built into devices such as smart speakers.
Good. Alexa? Oops, I lost it, sorry. Let me reconnect again. Alexa? Who is Ruhi Sarikaya?
Ruhi Sarikaya is the Director of Applied Science of the Amazon Alexa team. Ruhi and his team are building my brain and my capabilities around ranking, relevance, natural language understanding, dialogue management, contextual understanding, personalization, and end-to-end metrics.
So you see, I'd better be looking for a new job soon because the digital assistant is doing a pretty good job. Alexa, what is his background?
Prior to joining Amazon, Ruhi Sarikaya was a principal science manager and the founder of the Language Understanding and Dialogue Systems Group at Microsoft. His group has built language understanding and dialogue management capabilities of Cortana. Before Microsoft, Ruhi Sarikaya was a research staff member and team lead in the Human Language Technologies Group at IBM Watson.
Okay, one last question. Alexa, what is his academic track?
Ruhi Sarikaya received his BS degree in 1995 from Bilkent University, his MS degree in 1997 from Clemson University, and his PhD degree in 2001 from Duke University, all in electrical and computer engineering. Ruhi Sarikaya has published 120 technical papers in refereed journal and conference proceedings, and is inventor of over 70 issued and pending patents.
Impressive. So, enough geek playing. And now to the real thing. Please join me in welcoming Ruhi Sarikaya for his talk.
Okay, all right. All right. Good morning, everyone. Thanks for coming this early. I'd like to thank the conference committee and organizing committee for inviting me over here. It's a beautiful city, beautiful weather, beautiful venue. And I think the team is doing a fantastic job. The conference is running like a well-oiled machine. Kudos to the team. All right. So, okay. I structured my talk into the following sections. I will first talk about human interactions with the physical and the digital world. And I will talk about the fundamental interactions, frictions that we face when we are interacting with digital devices, applications, and services. Then I will talk about how conversational AI works in the case of Alexa. And I will also provide some solutions, talk about the solutions to these fundamental frictions using conversational AI. So let's start with friction. You will hear this a lot throughout the talk. I looked up the dictionary and altered the definition of friction to target the problems that I will be talking about this morning. So friction is any variable that slows you down or entirely halts the progression towards achieving a goal. This probably happened to many of you around holidays, like Christmas time. You bought a present for your kids or your family members, and they opened the present only to find out that either the battery is missing or the cable is missing. And this is a bummer. And since this happens around the holidays, all the stores are closed. And this is not just about physical goods and gadgets. This happens when you are purchasing something online from web services. There are overly complicated forms that you need to fill out and difficult to navigate menus. It creates aggravation. And when this happens, customers, they never blame themselves or they try to figure out a solution. Instead, they abandon your website and they go seek out the solution elsewhere, your competitor. And according to the latest study, about 78% of the customers, they bailed out on a transaction and didn't do intended purchase because of these customer frictions. And by contrast, if the friction is reduced in a transaction, that creates a snowball effect. Imagine that you're coming here, you need a carry-on luggage, and you're visiting certain websites, and then you find a luggage, and right there it says that this luggage is suitable for carry-on, and if you order it now, you will get free shipping. And then it's a positive experience. You go tell this to your friends and colleagues. So I was thinking about, as you know, Amazon is active in many different business segments. AWS, e-commerce, even Amazon Studios and Alexa. So what does that Amazon really do? If you summarize it in 2 words, Amazon is in the business of removing friction. And one-click shop is about removing friction. Amazon Prime is about removing friction. And Amazon Go is about removing friction. I am in Seattle, headquarter 1, in Day 1 building. From 25th floor, it takes me 90 seconds to go downstairs to Amazon Go stores, grab my lunch, and come upstairs. 90 seconds. So that's about removing friction. And Alexa is no exception. And removing friction is a key to customer satisfaction. Let me ask you a question at this point. So what is the common thread or theme across these different types of frictions? Think about it. I think you will find the answer throughout the presentation. Okay, so let's go to the basics. So how do we interact with the world around us, physical or digital? So we have, our senses: sight, hearing, touch, smell, taste, and sight, hearing, and touch. These are the primary ones. And we perceive the world around us through our senses, and they're stored in different parts of our brain. So this is a simple computational model of human information processing. We get the input through our sensors, and then we process this information, and then we generate an outcome or response. So in this image, the visual signal from our retina is related to our primary visual cortex in the back of our brain. And the sensory information is combined with memory, knowledge, reasoning to come up with a response. And that response is actuated through our motor skills, which is essentially controlling our muscles and limbs. In this case, you see a pedestrian crossing the road, and we hit the brake. And this whole thing takes about a quarter of a second. Now, how about computers? Computers do not have senses. They don't have sight. They don't have hearing, at least until recently. And they need to perceive the environment, and we explicitly provide this input to them. And we do that through typing, touching, and primarily using our hands. And if you go back, this is actually the first computer. It's called ENIAC, and this is accepted as the ancestors of modern-day computers. And here, Francis Bilas and Betty Jennings are standing in front of its main control panel, and they're programming this machine. And there are about 40 panels and about 3,000 switches and hundreds of cables. So it took them a couple days just to provide the input for the types of tasks that this machine is supposed to do. And it took as many days to take it out. So it took about a week just to do simple things that you would do probably in a minute with 3 lines of code right now. So I want you to specifically focus on the input part of the computers, how they've been getting input from us and how we have been providing input to them. So this is Apple One, and it's built by Steve Wozniak in 1976 in the garage of Steve Jobs. And if you look at it, this is actually similar to the computers that we see today. It has a keyboard, it has a system unit, motherboard, and a screen monitor. And in 80s, we have IBM PCs. And 90s, we have Windows Desktop. With the invention of graphical user interface, we also added a mouse. You can scroll up and down, and you can click on the stuff. But still, you have monitor, system unit, and you have a keyboard. And this is what you have today, where keyboard, monitor, and the system unit are fused together. You have a single entity laptop that you are using. And right now, the keyboard has disappeared. It became a software. You still use hands, though, to maybe more touching and less typing, more swiping and touching. But still, the primary mode of providing input is your hands. And the problem with this is, when you look at it over the last 40+ years, the computers are designed primarily around the tactile input. And it is not designed receiving input from other modalities like voice or vision. So I will focus on the voice. And this is a problem. This is a problem because even though we have mobile phones, well, it's a computer that you go, and you can use on the go, you take it wherever you go. But whenever you interact with it, it binds you to the screen. It actually immobilizes you. And that's a friction that has to be removed moving forward. There is no good reason, actually, why you need to stop everything you do just because you're interacting with the computer. All right, so these are Alexa devices that we launched over the past couple of years. And as you see, there's only one device, or two of them, that has a screen, and the rest is headless. There is no screen. And there is not a single day that you hear and read in the news that goes by that you don't hear these types of news. And you may be wondering, and also trying to make sense of what is really happening. So I will provide my perspective on what is happening here, and maybe talk about the deep currents that are at play beneath the surface. So let's start with intelligent personal assistants. And what is intelligent personal assistant? It is a meta layer of intelligence, and it sits on top of other services and applications and performs actions and serves content and answers to fulfill the user's request. It also has natural language interface. This is actually a feature that the customers love, and we have done many research, and the customers love to interact with these devices through natural language. And it relies on a core set of technologies, capabilities like machine learning, AI, natural language understanding, inference, and personalization. So there are many intelligent personal assistants in the market. These are the main ones. Siri was launched in 2011, and a year later, Google came up with Google Assistant. Cortana was launched in 2014, and later in the year, we launched Amazon Alexa. And here's a real example. And actually, I was traveling to Prague, so I had this flight card on my phone. I booked this trip a couple weeks before. And this is at the day of travel. I get this notification card telling me that my flight is delayed. And when you think about it, these are the steps that the machine, the agent, had to go through. It scans my email, and it extracts the information, and it stores it somewhere, the flight information. It stores it somewhere. And it computes my current location using the GPS on my phone and checks the traffic conditions to the airport and tells me whether I should leave for the airport or not. And also checks the flight status and updates me with that information. And also, here, it knows that my target destination is Prague. It tells me the weather in Prague and also the exchange rate between US dollar and Czech currency. These are the information that I need to find out for my trip, but I have to use 7, 8 different applications. And the promise of personal assistance is, it can do these atomic steps behind the scene. It can stitch them together, and that provides a tremendous value to the customers and removing the cognitive friction that you have to go through. The composing different tasks and different steps to get you an answer. Now, I will spend 5 or 6 minutes and take a detour. And talk about what's happening in this space during the past 50, 60 years. This is a chart that you may have seen. This is generated by Mary Meeker, who is a Wall Street Journal analyst, ex-Wall Street Journal analyst, and she's an investor right now. And I replotted here for you. So this is showing the computing cycles that are taking place every 10 to 15 minutes. It started in the 60s with the mainframes in the basement of large corporations that you didn't know it existed. And fast forwarded to the 2000s, where you had the desktop in your home and in your offices. Right now, we are going through the mobile internet computing cycle. If you look at this graph, the y-axis is showing you the installed base. Basically, what it tells you that with every computing cycle, the installed base is growing by about 10x. With the mobile internet, we have around 10 billion units in circulation. And the next computing cycle is Internet of Things, and we expect it to have 100 billion devices. When you think about it, it really makes sense. Today, you have, say, a few computers, your smartphone, your tablet, and you may have a laptop at work, at the home. You may probably have 5, 6 devices. And starting now, you will have your fridge, your thermostat, your lights, you will be able to interact with them through natural language and have them to do things for you, because any device with an internet connectivity will be a computer. So the definition of computer is changing. And that's what I said. The mobile phones are dominating the market right now. Now, I will bombard you with a set of charts. Sit tight and bear with me for a few minutes. And this is the global computing device shipments in millions. And as you see here, the PCs are flat, maybe slightly declining, not good news for Microsoft. Tablets were rising, but then with the increasing the size of the form factor for smartphones, that sort of got tamed. And the smartphones are, as you see, it increased quite a bit. And it's saturating, though. Like this year in 2018, it's expected that 1.6 billion smartphones will be sold. And this is the global digital statistics. And as of 2018, we have 7.6 billion people in the world, and the unique mobile users are 5.1 billion. So when you think about it, anyone who's older than 10 years old could be a target market for smartphone. And that's about 5.5 billion people. So it's expected that in about 2 years, everyone in this target market will have a smartphone. So that means there's no growth for connecting the people through smartphones. But the big corporations has to grow. So what is the next big growth opportunity? All right, so that was the devices. Now there are applications running on these devices. And this chart is showing the applications in different app stores, primarily Apple App Store and Google Play Store. As you see here, there is no sign of slowing down. There are over 2 million apps in Apple App Store and over 3 million apps in Google Play Store. The trajectory is upwards. And this is showing the global app downloads in billions. Last year, there were about 180 billion apps downloaded. Again, if you look at the trajectory, it's going up. There's no sign of slowing down. And this chart is interesting. So this is showing you the app usage statistics, number of apps used per month, and time spent each of these apps. If you look at it, the blue chart here, that's fairly flat. From 2001 to 2017, look, we use on average about 30 apps in a month and 9 apps in a day. Even though, as I said, developers are writing many more apps, and people are downloading apps at an increasing rate, and yet we are not actually using these apps. Why? So 80% of these apps are called zombie apps, meaning that no one ever used them. So here is one app you probably didn't know that it existed. It's called P Times. So when you are in a movie theater and watching a movie and you need to pee, so you can download this app, and this app will tell you that what is the best time to pee. So So human editors, they sit down, they watch the movie, they sit down and they annotate the movie. Then between 12 minutes and 15 minutes, there's no action. You're not missing anything. You can safely go pee and come back. So, so the point is, there are many apps like this, which you may argue it's not useful. There are many thousands of, hundreds of thousands of apps that are very useful, but you just don't know those apps. So app discovery is a challenge. It's actually a core challenge that we haven't cracked so far. So that's friction number one. The other problem is, to figure out how these apps work. Say you are using Facebook app every day. So if you never used Facebook app and I give you the Facebook app, it will take you at least a couple hours or maybe a day actually to figure out how this application works. Now imagine that you have hundreds of thousands of these applications. You simply don't have the bandwidth. You don't have the time. You don't have the cognitive bandwidth to learn how these applications work. So that's friction number two. That's something that we haven't cracked either. Now, let me ask you a question at this point. What is the most valuable asset you have during the day or any day? Okay, you got the answer, time. So I will come to what 1,000 minutes is. So here's another chart. This is actually showing, this is for US households, US people living in the United States. It's showing how we spent our time between web, mobile devices, and TV. Something interesting happened around 2014, where the time we spend in these mobile apps surpassed the time that we are spending watching TV. And when you look at the, from 2014 to 2010, last 4 years, you will see there's about 110 minutes difference. And where we are spending time in these applications. Let's take a note of that. And these applications are after you and your time. That's what makes them valuable. And here are two charts. Can you tell me the difference between these two? You have 5 seconds. Let me give you 10. No? Let me give you the answer. 6 years. That's the difference. Well, remember in the previous slide, I told you that there are 110 minutes difference between 2010 and 2014. And if you look at this chart, as if nothing has changed, we sleep, we work, we care for others, we do household chores, and nothing has changed in the last 6 years. So the math doesn't add up. So 1,000 minutes is your daily budget. If you leave out the sleeping time, which is about 7 to 8 hours, that leaves you with 1,000 minutes. When you think about it, you need to work, you need to eat, you need to, as I said, do shopping, clean the house, take care of the kids, everything. It has to fit into 1,000 minutes. That's not a lot of time when you think about it. So what does that mean? Well, this is what happens. This is, you're having fun, so to speak, with your friends and colleagues. So the application apps penetrated anything, everything, whatever you do. And this is all too familiar scene, right? Maybe not. So what this tells me is that you are well over your 1,000-minute budget, and you need help. You need help for managing your life. And this is what Alan Turing said, one needs a machine to beat another machine. Intelligent personal assistants could be that machine that will give you your time back. At least this is the promise. Now, another point here is the natural way to interact with the personal assistants is the voice input. And the reason for that, there's actually a core reason for that. When you look at these smart devices, you type, you touch, the information throughput to these devices would be 4 times faster if you speak to them as opposed to you type to these devices. And you realize that you're already doing this with the improvements in technology, that whenever you see a box with the mic icon, you actually hit the mic and you start speaking as opposed to keep typing. And the reason for that is, speech recognition improved quite a bit, and it's expected to replace touch and typing as the primary input form. Touch and typing will not go away, but I'm saying that it will be the primary input. And because of this, the big companies are recognizing it, and they push deeper into the platform for Apple, Microsoft, Google. And there are several projections, and I've been keeping track of these. Actually, they're not off. They're conservative. And, in the next 2-3 years, all searches will be, 50% of searches will be voice-based. And the deep learning had a huge impact on speech recognition accuracy. Even there's a task called switchboard telephone speech recognition that I've been following closely. There's a competition between IBM and Microsoft. speech recognition systems actually can outperform human on certain tasks, which are very difficult. And Amazon Alexa is entirely voice-driven, and customers are loving it, and it's adopted, and the usage keeps increasing. So, now if we bring everything together that I said so far, so in about 2 years, 3 years, almost everyone will have a smartphone. And you spend over 3 hours in a day, and it's still increasing on your smartphone. And Internet of Things is happening with no clear and effective way to interact with these devices. And the frictions that we listed are application discovery, limited cognitive bandwidth to learn how these applications work, and information flow into these small form factors and IoT devices. And the constraint is critical. That's your time budget, 1,000 minutes. So Alexa aims to address these frictions through machine learning and AI, and it provides a layer over applications and services to find the right skill, right task for you. And it can do it proactively without you asking, or it can do it reactively based on your request. So now let's go back to how conversational AI works in the case of Alexa. So when you say, Fabian tried it here, when you ask Alexa, what is the weather? So there is a wake word detector running on the device. So unlike what people think, actually, not everything goes to cloud. The engine running on the device just listens for the keyword Alexa. And once it hears Alexa, it starts streaming the audio to cloud. So that goes to the platform, and platform takes this utterance and sends it to speech recognition service. And speech recognition service returns the recognition results. It transcribes the speech, and the platform sends that to an LU service. And an LU service basically extracts the meaning from this utterance. What is the user's intent? What are the entities that the user talked about? And after that, it finds the right, we call it skill, you call it domain, some others call it answers. These are basically the units that takes the NLU output, and like as in the case of weather, you may call the AccuWeather or something else to get the information that you want to serve to the user. And that goes back to the platform, and it also sends a speech directive, meaning that this is the weather in Lyon is 23 degrees and sunny, and the directive is played, first actually synthesized through text-to-speech synthesis, and then that's sent back to Alexa voice, and you hear that in the Echo device. So this is sort of the full path that you go through. Of course, this is simplified. The real systems are a lot more complex than this, but I think this gets the idea. All right. So this is we have. As you know, we are building these capabilities to Alexa, but we have an open platform where if you own a hardware or if you manufacture hardware, you can bring Alexa's speech recognition and natural language understanding capabilities to your device. And you do that through Alexa voice services. These are a set of tools and APIs that you can use to bring Alexa's voice and intelligence to your it's even smart speakers. Other companies are producing smart speakers similar to Echo. The other side of this is Ask Alexa Skills Kit. In this case, you can, if you have a web service or you have a use case, you can actually bring that to Alexa. Say you're Domino's Pizza, you want Alexa's customers to order pizza from you, you can actually build a skill within hours. And Alexa would be the endpoint. The customers can interact with your skill, and you can take the orders. So these are the two. It's fully open, as I said. The number of skills are growing day by day. And so now, this is, Alexa Brain is the team I've been leading at Amazon. And our focus has been about removing natural language interaction frictions. So I will be talking about these 3 circles here. We have actually a lot more circles, but we are going to be making an announcement today. By the end of this talk, we are going to have a blog post talking about the features that I will be talking here. And they're related to skill ranking and arbitration, and multi-turn dialogue, contextual understanding, and memory and personalization. So the first thing is, as I said, the interaction with the skills, the core frictions that I mentioned. So we took this problem head on. And because Alexa is voice forward, can we eliminate or reduce, at least, the app discovery? That the customers, they don't need to know what application is right for their request. They don't need to know how they should interact with these applications. If you remove these devices, these hurdles, these frictions, all of a sudden you go from, say 50 to 100 first-party domains to 40,000 domains that the developers are building and adding every day. So all you need to do as customer, just state your intent in your natural language, and we will find the right skill for you, and we will get the answer from the skill and give you one-shot answer. And that's the problem we took on. And as I said, this is addressing the friction number 1 and friction number 2 that I described earlier. And the other one is contextual understanding. Most of these personal assistants are designed around single shot interactions. You ask them a question, you get an answer, you're done. And there are many tasks and scenarios that it requires multi-turn interaction. And that's the ability to carry over the context from one turn to the other. So that's another announcement that I will be making. And that's another problem we took on, by the way. And the last one is memory. So, you interact with these assistants every day. They learn not fast, So, because it's a long, you get the data, you transcribe, you annotate, and then, you update the models to sort of see the improvement, but at a slow pace. Can we, we thought, can we actually add memory to Alexa so that it learns better? It learns faster, so it remembers things for you. So of course, there are different stages of this. We first started with, if you ask Alexa explicitly to remember certain things, then Alexa should remember those. So that's the last feature that we are announcing. And as I said, by 9 a.m., this should be live. OK. Now, let me talk about the complexity of the problems. These aren't actually simple problems. Natural language skill interaction challenges. So let me talk about the ambiguity first. So if I say, Alexa, what should I do for dinner? What do you think Alexa should understand? What is the user's intent?
Well, you're hungry, for one thing.
All right. Well, you may be hungry. You may want to book a restaurant. You may want to order food, or you may want to find a recipe. It depends, right? If you're cooking at home a lot, you may, you expect Alexa to suggest your recipe. If you're ordering food a lot, you expect Alexa to do something else. So it depends. It depends on the person. So here's another example. Alexa, find Hunger Games. Same, right? It could be playing a sound trail, or playing video, or playing audiobook, or buying an item. You don't know, right? And this is interesting too, that Alexa schedule a package pickup for 6 p.m. For sure, you know that this is UPS or FedEx, but which one? Right? It depends. It depends on your time and location, and also your zip code, because they may not serve your zip code. If you're asking this at 6 p.m., maybe FedEx handles it, not UPS. All right, so you sort of got the idea. So there is this natural language ambiguity that you can't really tell what is the user's intent. You can sort of narrow it down, but you can't really tell what it is. So this is a problem that we need to deal with. The other one is, with the third-party skills, the current interaction model, there are exceptions to it, where we took the path of how quickly we can integrate these third-party applications to Alexa. And the model that we choose, it worked very well, by the way. We have over 40,000 skills right now. you can integrate the third-party experiences to Alexa, skills to Alexa by saying, Alexa, ask X to do Y. So there's a strict pattern there, the phrase, Alexa, ask X. That sort of handles the ambiguity I'm talking about. You actually narrow it down to one specific skill. That's Alexa, ask X. And then Y is the payload that the skill needs to understand and come up with an action. And the problem is, this is not natural. This is not Alexa, how is the weather? I don't need this Alexa, ask blah, to tell me the weather. And we did a study internally, and we found out that 81% of the low skill usage with respect to first-party domains, are attributed to interaction with the skills, the skill discovery, awareness, and frictions around invocation and recall. And this is an example that actually with this announcement that I made, this is what will happen. So when you ask Alexa, how can I remove the oil stain? And for the first time, Alexa will find the right skill and tell you that Tide Stain Remover can help you with that. Do you want to enable it? We want the customer's consent to enable the skill. And the customer says, yes, please. And the second time you use it is for the same utterance. Alexa, how can I remove oil stain from my shirt? This time, Alexa will tell you, OK, Tide Stain Remover will help you with that. And we hand it over to Tide Stain Remover. In one shot, you get the answer to your question. There's no multi-turn step. This is actually foundational when you think about it. And the number of skills are growing. And you will be able to interact with these skills in a natural way. All right, so this is now I'm talking about the solutions, more on the science side of what we have done. And this is the high-level architecture of the system that we have in Alexa. And the green boxes are the new components that we introduced. And we introduced the NLU shortlister, and I will talk about what it does. And we also introduced the contextual ranking. So this is the NLU shortlister. If you think about the ambiguity that I talked about, Alexa, what should I do for dinner? So there is not a single skill that will answer this question. So what NLU shortlister does is, for this utterance, what are the likely skills or domains that can answer this question? And when we designed the solution, there were a few factors that we had to keep in mind. And one of them is, the number of skills are increasing every day. It's 40,000, maybe 100,000, 200,000 in the next year or two. So the architecture should be able to handle that scale. That's one. The other one is, there are new skills added. So each time we shouldn't go and retrain the whole thing. These are more practical things, but they're important if you're running a production system. You should be able to add these skills incrementally without rebuilding the whole system. The other constraint is the memory and memory usage and footprint. We should be able to minimize the memory required for adding a new skill. So and also accuracy is something that we optimize all the time. So when we thought about all these factors, this is the architecture that we came up. So we take an utterance, and this is a bidirectional LSTM at character level and word level. The box that you see here essentially does the utterance embedding using the characters and the words in the sentence. And this is largely skill or domain independent. And this embedding comes up with this green units that you see here, say 200-dimensional vector. And we take this vector, and on the left side, you see the skill enablement. This is personalization information. It's actually more than this, but we are just looking at the skill enablement as personalization signals here. Customer A, enabled skill, A, B, C, some other customer enabled some other set of skills. So we use this information when we are shortlisting the skills, because if the customer enabled these skills, that's a strong signal. And we do that through attention mechanism and also personalization signal before we do the classification for the skills. We take the embedded utterance embedding, we combine it with the skill signal and also attention over the skills. And then here what you see at the top is these are per skill feed-forward layers. So it's binary. It's yes or no. And as I said, the dimension of this vector is, the embedding vector is 200. So 200 by 200, that's about 400 parameters per skill that you need to learn. And when you do the math, actually, you can have hundreds of thousands of skills, and you can be still within the memory limits of a GPU. All right. So this is something that, we published this. Actually, it's just got accepted 2 weeks ago. We heard that it's a paper that you will see it in ACL. It's a long paper. So these are the results that you will see. There are more results in the paper. So we took 1,500 skills for experimentation. And we looked at a bunch of different models and model architectures. And binary is, if you train a separate model for each skill, these are the set of results that we have looking at top 1, top 3, or top 5 best results. And you multi-classes, you still do the embedding, but do the classification, N-way classification at the top layer. And multitask is you still do the embedding, but instead of multitask classification, you classify each skill independently. And one bit flag is this personalization signal, whether this skill is enabled or not. We add attention to it. So the takeaway message here is, let me get to it. So when you do sentence embedding, that's multitask, you get better results. And if you add the personalization signals of both, as a bit and also attention, you get further improvements in the results. And looking at the model training side, this was important also, as I said. If you train a binary model, it takes 34 seconds. And expand is what we are trying to do here is, you already trained a base model, and now you're adding skills incrementally. That's what we are looking, and we are looking at the training time. And adding a new skill, you just add a new skill in 30 seconds. And if you do complete refresh of the models, that takes about 2 orders or more time to train the whole thing. The accuracy is, as you see, not different, expanding versus refresh. Okay, I covered that. So this is the contextual ranking part. It's 2-stage ranking. We shortlist, we run NLU, intent recognition, and entity recognition, and entity resolution. Then we do final ranking, which takes all the contextual signals that we have about the session, about the user, about the device, and then we do final ranking. And here, the user said, play Michael Jackson, that we shortlist that these are the classical music, pop music, whether these are the likely domains that can answer this question. We run NER and intent classification. Then, as I said, we generate the hypothesis that would be ranked. So if we look at this box here, so what we did here is, we generated these hypotheses, these all embedding. This is, again, LSTM. And we tried to model the dependencies and structure between these different hypotheses in the shortlisted skills. And these are the results. So here, what you see, the first line is if you're looking at just shortlisted output, which is non-personalized. Small scale is typically this is what people have been doing and reporting numbers in the community. And we are going to 1,500 skills here. Of course, because of the ambiguity, the accuracy drops from 95 to 81. And then when you do the hypothesis ranking, as I said, getting these contextual signals, you can get to 85 and 95. And then when you model the dependencies between the different hypotheses, you get to 97 and 93. And here, LSTM-CH this is if you, manually author some of these features, and you get something similar. The point here is you can actually learn these dependencies and these features. You don't need to manually author any feature. And okay, so the other problem that we looked at is, and this is actually coming out in Knuckle, also the 2 papers. And contextual carryover and resolution. So this is about carrying over intents and slots across user turns and system turns. This can be within domain or cross domain. So slot carryover example here is, user said, Alexa, how many minutes? 3, okay. This is actually last 2 slides, okay. Yeah, so it's a multi-turn interaction. There's a user turn, there's a system turn, there are slots and entities in different turns. Can we actually carry over or drop this information so that we can accurately answer the user's question? So this is, we lost it, okay. This is the example here is, Alexa, how is the weather in Seattle? The next turn is Alexa, how about this weekend? Alexa, how's my schedule? How about this weekend? The same utterance, second turn. You shouldn't give the same answers because the first turn is different. And the challenge here is each of these domains, they don't share the same schema. They mean different things for the same entities. So in order to solve this problem, we came up with, again, another LSTM-based architecture. It's basically looking at the user utterances, system utterances, and we try to find the right slots and how to fill them, given everything that we know. And I can go skip that too. So we run some experiments. Basically, what this is showing is, we can, using decoder encoder LSTM network, we can get pretty good results. And it's also within domain carryover is a lot easier compared to cross-domain carryover. Those are the key observations. And Alexa memory is, this is, as I said, Alexa will remember things for you so that you don't need to remember. So you can say, Alexa, remember that, like Julie's birthday is July 2nd, and Alexa, I gave my nephew a Batman logo for his birthday. And when you ask, there is a retrieval part, you can ask Alexa to retrieve these memories. So I think the point here is, in your household, okay, where is the car keys? Where is the passport? Instead of asking this to your spouse, you will ask Alexa. Did you check with Alexa first? That's where we want to get to. And these are sort of the numbers that we have on this experimentation. So, okay, these are, I will leave you, no, maybe, yeah. These still, we haven't solved all these problems. There are speech recognition problems, arbitration problems, scaling issues, end-to-end metrics, measuring these experiences. I'd like to end with this slide on a positive note. It's still early days, and we are really scratching the surface. I'm very excited about the future. As we say at Amazon, it's still day one. Thank you.